Thank you for coming. Today we're going to talk about one of my favorite and least favorite data types, the vector. And contrary, I've given variations of this talk before, so for those of you who've seen it, this is going to be a little bit different. Given the theme of PGConf.dev, this is going to be more about lessons learned, implementation, and future direction as opposed to usage. But I did want to start off a little bit just talking a little bit about how vectors are used and why is this suddenly so important that we're spending all these time and resources trying to better support this kind of data. So that being said, the quick agenda is we'll do an overview, just like why do we care, why is this such a big deal? And then really ask the question, like, why do we even use Postgres for vector similarity search? Like, why, there's a lot of, all these other solutions out there. Why Postgres? We'll look at the year in review of PG vector development because a lot has happened over the past year that has actually helped to answer that question, but there's still more work to do. So we'll do a little bit about in terms of where things are going. And just real quick, there's going to be a lot of content to cover in the next 50 minutes. We will have time for questions at the end, so please save your questions and your booze until then. And without further ado, why vectors? Why do we even care? And the long story short is that there has been a revolution in AI and machine learning. And my 30-second summary of it is that myself, coming up as an app developer, it's just so much easier to use these models now. Fun fact, I actually did study machine learning in college back in the mid-2000s. I thought like this was the field I was going to go into. Simultaneously, I also loved using databases. But as I was studying it, I was like, oh, all these models are ad hoc. I'll have to build them all on my own. I need a PhD in it. I'm losing patience. I just want to go out in the startup world. And some questionable decisions there. But the point is that nowadays I can just make an API call and I can get this like highly enriched machine learning answer. But to build these machine learning models, while it's certainly more accessible and easier, particularly with a lot of the ones that are available, even as open source models, it requires a lot of CPU and GPU power, as Dr. Seltzer alluded to yesterday. But there's this wonderful technique that's been developed that can basically reduce the overall cost of doing that, and that's called retrieval augmented generation. And where retrieval augmented generation, or RAG, is really good is that you can take data that you already have in a private data set or in some other database and leverage a foundation model to be able to build that out. So for example, I had a store where I was selling blue elephant vases, and if I go to like one of those public foundation models and ask, how much does it cost, it doesn't know, right? Because it's in some private database somewhere. But by using RAG, what I can do is I can take data that exists in a database, use it to augment the response, and find out like, oh yeah, this this blue elephant vase costs $20. So vectors have a very specific portion of the workflow, really in two parts of RAG. The first thing you need to do with RAG is you need to basically take your raw data and transform it into this representation, in which case is a vector, and store it in a database. And then part two is that you have someone come to your application and say, hey, how much does that blue elephant vase cost? You need to be able to take that information and turn it into a context or like some common representation of it, which also happens to be a vector that is generated from a machine learning model, in this case an embedding model. You perform that lookup on the database, you get that information, and you put it into the foundation model to get the final response. So vectors are used in two parts. Quick aside, do we have to use vectors for this? Like, why can't I use other search lookups? You can, and that's like actually one of the things about it is that there's other ways that you can get this information. One of the reasons why vectors are used is that it provides effectively a common language for being able to handle different information coming from different systems, and you're effectively mapping your raw information to the same machine learning model based upon how you're using it in your RAG workflow. But there's some challenges working with vectors. The first challenge is that it takes time to take your raw data and put it into one of these embedding models. And even as these are getting faster and faster, there's overhead. And let's say you have like 1 million pieces of data, and it takes 100 milliseconds to generate your vector representation from it. Well, 1 million times 100, which is too big of a number for me to calculate right now. They're also quite big. Just taking like one of the standard sizes we see out there, 1,536 dimensions, which I'm going to shorthand to 1,500 dimensions, and you have these vectors tend to be 4 byte floats. So again, 1,500 times 4 is 6 kilobytes. And for us database folks, particularly us relational database folks, That's a lot of data just like packed in like this one little representation. Typically, row size for database is in the byte size, right? When you see a lot of things that are being stored. But here we have a payload that's 6 kilobytes, which means it quickly adds up. So your storage, I had a highly used transactional database. For me, was big. It was like 30 gigabytes total, and that was over like years of collecting data. And here with just a million rows, which is like nothing compared for me in that database, there's like 6 gigabytes right there. Well, we could try to compress it, except we can't. Have you ever tried to compress random 4-byte floating point numbers? Yeah, and in fact, if I'll skip ahead. If you try to use toast on it, you actually end up with a larger value than what you started with. So you can't really compress them. And there's some techniques we can use to reduce it, which we'll talk about later. But even if we could, the other thing is that in order to perform the fundamental operation of comparing vectors, which is a distance calculation, you have to look through every single dimension in the vector. Like you can't just look at the first half and say like, oh, I'm good to go, because the last half could end up skewing the distance between them. So there's no shortcuts. The final bit is that when you want to find a similar vector between every other vector in a data set, you have to look at the entire space. So effectively every single row in the table in order to figure out which vectors am I most similar to. The good news is that there is a shortcut for that. So that, the regular technique, we know it as k-nearest neighbor. The cool kids today call it exact nearest neighbor. But there's something called approximate nearest neighbor, where I don't need to look over the entire data set to be able to figure out what is my best available vectors. The nice thing is that it's a lot faster. If I have to do only 50 lookups versus a million lookups, typically 50 will be faster. But this introduces a concept that's really weird for us database folks, which is called recall, which is your percentage of expected results. It's a little bit different than accuracy, because your recall could still be high and your accuracy could actually be a little bit lower, because with accuracy, we care about exact ordering. With recall, we just want to see that given 10 results, we get 8 of the expected 10 results, and maybe they're not in exact order. So it's not, you're going to see in a lot of the benchmarks out there for vector search that recall is a measurement of it. In fact, if you're seeing something and they don't talk about recall, I'm very suspect of that benchmark. But this is something for us to keep in mind, because it does affect the overall user experience of using vector search. So as we go through this, there's a few key metrics I want us to all consider, kind of like to speak a common language. The first is the index build time, because we're going to see that how much time you spend building an index typically translates to the quality of search you have, particularly getting very fast searches at high levels of recall. But also what impacts it is the index size. Already we're seeing that if we have these vector payloads that are 6 kilobytes and we index a million of them, that's a million times 6 kilobytes, which is, again, very 6 gigabytes right there. We have to account for recall. But then we also want to look at query throughput, like how much load can we throw at one Postgres instance, be able to maximize these searches, and also understand the query latency. And typically, we want to look at P99 latency, because that gives you effectively the upper bound of it. If your P50 is low, great, but let's see how we're doing in worst case scenarios. Which leads us into Postgres as a vector database. So this term vector database is being thrown around a lot. And to me personally, it's nothing new. What is this? JSON, right? It's not a trick question. So remember, back in the day, we had these web apps, spitting out JSON documents, and you would take this JSON document, you'd map it to your relational model and store it in a database. And some folks had this brilliant idea. Well, why don't we eliminate that whole relational mapping and just store that data directly in a database? Good idea, right? One less step. Who needs databases? Who needs relational databases when you can store JSON documents directly? And you can see, kind of the history here that JSON emerged at this data type, at the turn of the millennium, and in part because of how web techniques advanced, we saw. I mean, for one thing, JSON was very easy to format, and it was very easy to be able to put this information, manipulate this information in web applications. I'm going to long story short this because I think a lot of folks in this room know where this is going. Postgres added support for JSON in 2012. JSON became part of the SQL standard in 2017, and Postgres has been implementing it since then. But the idea is that JSON is a data type, and certainly there's certainly merits of storing JSON in special databases for it. Postgres still has some functionality it needs there, but For a lot of things, it's very common and very easily accessible. So if JSON is just a data type, well, vector must also be a data type, right? At the top, I said it's a nasty data type, and I'm trying to convey like why I think it's nasty, but because of that, it's just a data type, so we can use Postgres for vector searches. But why? And I think the biggest reason is actually the first reason right here, is that there's so much developer tooling built around Postgres. I mean, that's really how I interfaced with Postgres for many years. I became familiar with SQL mostly out of necessity because I'll make a confession. I loved using ORMs. They're very easy. I could build things very quickly with them. But because of that, it's because the tooling is available and it makes it very easy for me to build applications. And beyond that, I'll skip to the end part of this, which is that Postgres is a database that provides ACID guarantees. And an interesting question that I've been dealing with is like, well, why do I even care about ACID for these kinds of searches? Well, I'll try to enumerate it. So one property of ACID is atomicity, basically all or nothing. If I'm going to store something, well, can I store it in the database? And it makes sense. If I'm doing some kind of bulk loading procedure or I'm doing an operation across a broader set of data, I want to make sure it actually gets stored. And if something fails during it, roll back. Consistency. I have rules in my database. I want to make sure that whatever I'm storing in the database meets all the rules that I have in it. Isolation. And this one is very interesting because I think a lot of folks miss this one because there's two things I think Postgres gives us here. The first is I'm seeing the exact view. When I run a query, I'm seeing the exact data that's available at the given time within that query. So effectively, I'm getting the accurate representation of my data. But also, and this is a key point, is that as soon as data is inserted and committed, it's available. And that's a really powerful notion because you see a lot of systems that don't do that. And there's a delay in terms of having that data available. And last but not least, durability. If I say a transaction is committed, my vector is stored and it's there. And this is really the most important one, that if you're building a Postgres extension for vector search, you want to make sure that when you say hey, this data is stored, it is stored. This is really the most powerful property of Postgres here. And I say that vector extensions because actually, what's interesting is Postgres has actually supported vectors since the very beginning. That's the array data type. This was around back in the Berkeley days. It didn't have the distance operations. The cube extension did. But the cube extension works only up to vectors of 100 dimensions. And as we see already with these newer machine learning models, they exceed well beyond 100 dimensions. So this whole ecosystem of extensions has popped up. And I'm not going to go through every single one because we're short on time. They each have some different takes, some different properties on it. But we're going to talk a lot about pgvector today, in part because it does support all the ACID properties of Postgres. And in part, well, it's kind of popular. This was pgvector last year. Was this pgvector beyond last year? But notice last February is about 1,200 likes on GitHub. And now it's at almost 10,000 likes on GitHub. And it's kind of keeps going up. I don't really see much of a slowdown in this graph. But again, what's a star worth on GitHub? Is there other stats to show popularity? Yeah. So Llama Index, which is one of the popular frameworks for building generative AI applications along with LangChain, has public stats. And I checked it the other day, and pgvector is their #2 downloaded vector store. And again, I'm using the best I can with public stats, but this is really telling that you have pgvector ahead of specialized vector databases. This wasn't a given. Why did people, this is back in April 2023. This was on the SIFT 128 Euclidean dataset, which is 1,128 dimensional vectors. And pgvector is at the bottom. So it's wait a second. When we think of Postgres, we typically don't think of a slow search experience. We think of, well, an easy search experience, but typically things are very fast because we often, for transactional applications, we don't want slow transactions. So why did this happen? Why is pgvector so popular? Now, I'll break it into two different eras, yesterday and today. Yesterday in 2023, I think one of the main reasons people want to use pgvector was that it was there. It's in Postgres. This is a powerful notion. It's, we like using Postgres. Developers like using Postgres, so if it's there, cool, let's use it. But the other thing is that tooling point, that the pgvector project made native implementations for a lot of the different drivers. One key representation is just being able to take these vectors in their binary format and transfer them over the wire in binary format to Postgres. Because if you have to go from binary to text to binary, that's a costly operation. But having just native binary to binary support really speeds up ingestion. I think in one case, like 3x. So having that certainly helps. Fast forward to like 2024, there's been a lot of work done in pgvector to go from that bottom of that chart to competing with folks up in the top of that chart. Performance is ultimately key. You might come for the usability, but you're going to stay for the performance. And it's an actively developed project. We're going to see contributions from all across the community. And I'll note that Andrew Kane, who's the lead maintainer of pgvector, has done a phenomenal job with the project. Like, he's added so many of the features we're going to talk about. But because there's community buy-in to it, that's really what's helping advance it. So let's do a very brief year in review and then get into some specifics. Because the fun part here today is that we're going to focus less on the use cases and more on the implementation. So rewind a year ago, when pgvector's popularity started to rise, it had an indexing method in it, IVF_flat. And we were starting to optimize it for the real-world use cases. There were some issues with plan costing where you'd flip from using the index to doing a sequential scan very quickly, and your query times would go from, say, like 50 milliseconds to 5 seconds, which is not a great developer experience. But we fixed that, and we started learning from users like what really matters. And really what matters was that they needed faster queries. There's all sorts of research going on all sorts of different indexing methods for vector searches. One that has emerged as being very popular is HNSW, Hierarchical Navigable Small Worlds. And we're getting into that in more depth in a few slides. But that was added in the version 0.5 release. And that certainly helped advance the pgvector performance goals. But remember, index building matters. We're going to see that the more time you spend building the index, the more likely you're going to have not only very high quality searches, but very fast high-quality searches. And that's what the version 0.6 release did, was that it made the index building a lot faster. But as we keep seeing, these data sets are growing. We need to figure out how we're able to manage the size of the overall data sets, but not take up too much space on our disk. And that's where the 0.7 release came in, was being able to handle these larger vectors that are coming from foundation models while reducing the overall data footprint of your pgvector data. So let's talk about indexing, because this is really the heart of what pgvector does. It's not that hard to have a vector data type, frankly. We've had that from Postgres since, again, like 1986. The hard part is searching over it. And the first thing you need to know is that I said no shortcuts up top, but there are some shortcuts. And we want to take as many of these shortcuts as possible to limit the amount of CPU time. Because remember, when we're comparing two vectors, we're comparing every single dimension. So any cycles we can shave off are great. The first thing that pgvector does when it indexes a vector is it tries to convert it to its L2 norm. Shorthand is we normalize the vector. I know for database folks, normalize is a loaded term, so I wanted to clearly define that. But effectively, an L2 norm vector means that if you look at the magnitude of the vector, or effectively the overall size of it, the magnitude, you basically reduce the magnitude to 1. When you reduce the magnitude to 1, there's some operations you can discard when you're doing your distance calculations, particularly around division. Division is still a very costly operation in your CPU. So if we're able to normalize those vectors, we have some shortcuts. The next thing we need when we index our vector are we need indexing techniques. And there's 2 of them available in pgvector today. There's IVF_flat, which is a clustering-based technique. And with IVF_flat, the key thing behind it is that you need to have all of your data really preloaded to basically build centers around it to cluster your data, and then ultimately you do your lookup over those centers, which we'll see in a few slides. The other one is HNSW, Hierarchical Navigable Small Worlds, which is a graph-based indexing algorithm. And I'll pause real quickly because when HNSW was added to pgvector, some folks were confused. Like, what do you mean like Postgres can do graph-based queries? Well, there's a few things there. So first, a graph is a superset of a tree. And databases are very good at tree-based queries, particularly Postgres. That's the foundational part of indexing. But because a graph is a superset, it also means that, well, yeah, we can include it in Postgres, that we have these index access methods that let us define custom indexing. And because of that, based upon how we implement it and choose to cluster the information, we're able to build the HNSW method to it. So the last key point about HNSW is that unlike IVF flat, you can add data iteratively, and it's going to position the data in effectively a good portion of the graph. With IVF flat, you can continuously add data to it, but it can end up skewing recall over time, and then you need to rebuild the index. So IVF flat has one index building parameter, and the reason I note that is that we are giving, normally when you build an index with Postgres, like you build a regular B tree, create index on table, blah, blah, blah. Easy for a developer, no thinking. I don't like to think when I'm building applications, I just want to go. We're going to see with these methods that our developers have to think a little bit more. And that's okay, but we should work on making it easier over time. So IVF flat is nice because there's only one choice. You have to choose how many clusters you want to build. So effectively, what you do when you're building it is that you run a k-means algorithm over it to find your centers over it. K-means is an NP hard problem, so there's an approximation k-means algorithm that's handled here. You build your centers, and when you search over it, you use a parameter called probes to basically pick how many centers you want to visit. Probes is what's going to impact your recall the most because, well, both list and probes impact it. But let's say I do one probe. It's a very fast search because I only have to go to one list, and I search over the vectors in those lists. But you might not actually get your closest neighbors when you do that. So let's say I expand to 2 probes. Well, I've increased my search time, but look, I'm getting neighbors that are much closer to me in that case. So this is the trade-off we're always going to have with any of these search systems is that no matter, the more that you search within the index, the better answers you're going to get, but it comes at a cost of query time. So the more that we can do upfront in building the index, again, the more likely we'll be able to be searching the space that we want. And one thing that we found, particularly from the app developer experience, is that HNSW tends to be a little bit easier in this regard because there's less thinking on this search. There's a little bit more thinking on the index building side because there are 2 parameters. So double the trouble. Every parameter you add, you're kind of exponentiating the decision-making process. So there's 2 parameters for HNSW. M is the number of links between the different vectors in the index. And E of construction is effectively your short-term memory as you're traversing the index and keeps track of the different vectors you've seen. With E of construction, typically the larger the value, the better the index that you're building. With M, it depends. For most cases, M equals 16 seems to be working, but there's certainly cases where it may help. It's usually more dependent on your embedding model. Actually, a quick side note there. A lot of what we're doing here when we're building these indexes is that we're overcompensating in many ways for the embedding model we're using, because if our embedding model gives us information that's very easy to cluster or it clusters very well together, we could probably use like very small indexing parameters because we always know that the search is going to go to like the correct area. So everything's kind of working in concert together, which also makes it a little bit challenging for our app developers. So how do we build an HNSW index? So let's say this is my space. The way that HNSW works is that it goes through hierarchies. Your type hierarchy is very sparse. There's a few vectors there, and you very quickly find which one I'm closest to, which you might not be very close to at all, but the idea is that you keep going down the hierarchy until you find vectors that you're closer to. And finally, at the lowest level, you're going to build out the most links amongst your vectors, and the idea is that you're in this neighborhood now that is very close and clustered together. When you do a search, it's actually very similar. The build process is similar to the search process, but in this case, you're not trying to connect yourself to different vectors. You're just quickly trying to find the ones you're most similar to. But the idea is that I have an entry vector. I see how close I am to a vector on the graph. I go down to the next level of the hierarchy. I find the next vector I'm closest to. I go down to the next level of the hierarchy, and I find the vector I'm closest to, and we're done with the search. And if we're maintaining that EF search parameter, we're effectively keeping a whole list of vectors that we're closest to that ultimately get returned as part of the query. So those are the 2 methods in a nutshell. Now, one enhancement that's come recently in PG Vector is something called quantization. What is quantization? So keep in mind, a lot of these embedding models, when you're getting the vectors out of them, they are 4-byte float arrays, effectively. And that can be a lot of information. The idea of quantization is that we're reducing the amount of information available. So for example, PGVector07 added one kind of scalar quantization. Scalar quantization is a technique where you're reducing the information while still maintaining the original data structure and the dimensions. So maybe another way of saying it is like I might map to a smaller floating point value, or I might map to an integer value. But I'm not changing the overall structure of the vector. I'm just reducing the information there to try to shrink it. So if we quantize to a 2-byte float, effectively we've half the size of the vector. If we go to a 1-byte unsigned integer, which is a popular technique, currently not supported in PGVector, but I do want to throw it out there. Well, effectively, you've gone to 1/8 the size of it, if I did my math correct. Yes, 1/8 the size, or 1/4 the size. I have trouble doing computations on the fly. Now, there's an extreme technique out there called binary quantization, where you can take your information and go to either a 0 or a 1. The idea being that if your vector is above 0, map it to a 1, below 0, or at 0, map it to a 0. That's one way to really reduce the size of your data set, but there are trade-offs to that, which we'll see. So this is relatively new. I do want to cover this use case real quick. Postgres has a wonderful feature called expression indexes. If you have an immutable function, you can use it in an index and basically cast to whatever value you want. So in this case, with PGVector, you can keep your original vector in the table and then the quantized vector in the index. So if you ever need to search again over the original vector, you can do that. So this is an example of doing it with scalar quantization, with going from a 4-byte float vector to a 2-byte float vector. Similarly, for binary quantization. And binary quantization is a very good case of where you want to keep the original vector on. So if you think about binary quantization, I'm taking this gigantic vector and reducing it down to this tiny little binary vector. But if you just do the search over all that data, you might find a lot of these binary vectors look very similar. In fact, you actually don't want to use binary quantization with any kind of vector. There was one data set, actually it might have even been the SIFT-128 Euclidean data set, where I used binary quantization and all the vectors looked identical. So I was getting terrible recall, but they were returning very fast. So this is why you got to look at all those different measurements. But what we can do in Postgres is we can re-rank fairly easily. And when we do the re-rank, what happens is that we find our light cluster of vectors, which they might all look very similar, but then we get the real vector back and we re-rank it and we get it in the correct order, which certainly helps improve our recall. These do have some advantages. Really, it's on build time. So this is the 2-byte float quantization. And we see that we don't really impact recall across the board, and we might actually get some performance benefits. But really, if I'm able to save space and get the same level of performance, that's called a win. So this is really good. With binary quantization, this is the data set that actually worked pretty well with it. It's the 1500 dimension vector. And we can see that we really shrink the amount of space available, and we shrink the build time significantly. But we do need to do a bit more work until we can get the comparable levels of recall. But it is possible to get the comparable levels of recall and be able to perform those searches. That being said, there's some limitations. Keep in mind, whenever you reduce information, you reduce information. You're not getting it back. So you need to decide, do you want to store a pre-quantized form of your vector in a table? Because keep in mind, we still have a double data problem here, kind of skipping to the end here. I have this gigantic vector in my table, and then I have this index vector in my index, which could be a gigantic vector, in which case I've doubled or more than doubled my, the total storage utilization. Or it could be a quantized vector, which certainly reduces the storage footprint, but it's still being doubly stored. And there's other systems out there that are just pure indexing systems where they don't do that. So it's actually one of the thoughts out here. I don't really discuss it further in the slides, but just throwing that out there that we do have a double storage problem that is worth considering. Are there ways for us to be able to better support that? And finally, some of these quantization techniques only work if you have larger vectors. But if you have a lot of data, eventually you'll have enough of these vectors that just all look the same, and it could impact recall. I don't have specific numbers for it, but this is one thing to keep in mind when you're using these techniques. So how did PGVector do over the past year? Now we're getting to implementation and recommendations. Well, for index build time, it's doing pretty good. Now, again, you have to look at where you're counting from, like the different axes, but the key bit is that if I go from the 050 release, and I compare it against using binary quantization on a data set where it's applicable for it, I'm getting 150x speed up in my index build time. That's pretty good. But even if I just take like a boring old like scalar quantization set or just doing nothing at all, I'm still getting around 30 to 50x speed up. Now, a lot of that comes from being able to use parallelization. That's kind of the cheat sauce there, but that's fine because if I'm instead of being able to build in a single core, if I can build using multiple cores and speed it up, that's going to have a very good outcome. Now, just one thing to compare here is before we had parallel build in pgvector, the guidance was if you need to build things more quickly, use a concurrent insert or a concurrent copy. And we can see that we can actually speed it up pretty well on a higher core machine. But the in-memory parallel build added in 0.6 really speeds it up because we go, again, from like hours to kind of seconds, in that particular case. And even though like the hour, like 2 hours is still better than 10 hours, it's a few seconds is certainly still better than a few hours. It's a little bit more than a few seconds down there, but you get my drift through exaggeration. So what's the net impact? This is my proof that index build speed matters. So using that same data set, here's and given these search parameters, we can see that in a serial build, well, first let me step back. So you have your recall. And we see as we crank up the EF construction parameters, our recall does increase, though we get to a diminishing return past EF construction 256. But we see that the index build time is increasing, fairly linearly, and we're in the scope of hours right now. But with parallelism, we still see we're increasing that. We still see that we have that same recall increase, diminishing returns, and we still see that we're increasing, in that way, but we've gone to minutes of build time, which basically means, hey, it's worth saying 256 is my default EF construction because, yeah, it's still increasing in build time, but it's dramatically reduced. Index build time matters because of that, we can get that recall bump without doing that much additional work. The other thing is now we have the ability to get smaller indexes in pgvector, which again matters. Using binary quantization on the applicable data set, we can be about 16x better. And with scalar quantization, which frankly across the board, the results have been pretty good overall, we can get a, 8x, 9x smaller data set on this particular one. So definitely worth considering. And finally, query latency. When I was talking with Andrew Kane on how to best describe this, he said, show it with higher recall. So a 99% recall, you're pretty close to 100% recall. And what we can really see is, particularly with adding HNSW, we really improved overall query latency there compared to IVF flat. Because IVF flat, to get that level of recall, we're doing this very broad search. And with that parallel query, it's very expensive. We've seen the recall gains are a little bit more incremental after adding HNSW, but they are increasing, and there are likely some more things we can do to better support that. Last but not least, throughput. The advantage of using a database that supports high concurrency is that you can use high concurrency. Here's some example throughput numbers on the. I think this is the SIFT128 data set. Expanded version of the SIFT128 data set. It's the big ANN data set. And we can see that it's scaling, pgvector has been scaling pretty well linearly. This test is a little bit older. I think this was actually on the 05 series, but that's still pretty good. And particularly at a recall value of effectively 90%, getting that kind of throughput is nice because in the real world, a lot of what I'm hearing is that folks are pretty good with recall between 80 and 90%. And Postgres is doing very well, on that level, particularly with the pgvector implementation in terms of how it clusters everything together. But there's always room to do better, and that's why we are here. One thing that we're always going to have to deal with the Postgres is what I call the 8K conundrum. Well, what's the 8K conundrum? The page size of Postgres is at 8 kilobytes. So everything that we need to do, we need to work within that 8 kilobyte size. But the nice thing is you can actually expand your heap size using a compile time flag. But a lot of people don't do that because if you don't have, they might not have access to the underlying binaries, or they just want to keep things standard to make sure that it can work physically with every other Postgres out there. It gets better. Even if you do change the size for the heap pages, it doesn't apply to the index pages. It is actually hard-coded. It's actually non-trivial to be able to get over that hard coding limit. Finally, this is becoming a very real problem very quickly because these vectors are getting bigger. Here are two common formats that you see here. And we recently have seen models that are using 3,000 dimensional vectors, which go well beyond the page size. So fortunately, we have quantization as a way to deal with that. But what if these vectors keep getting bigger? We can only quantize so far down within the page. But you're like, wait, Jonathan, there's something called toast. Like, didn't we hear about this all week? Well, yes, we have toast. Toast is our way of being able to store things out of line. And interestingly, if you use the Postgres defaults, you're going to start toasting relatively early in the process. There's 4 different types of toast. I'm just going to speed through this real quick. The 2 things that I see most frequently with pgvector are plain, which is I keep the vector within the table, and external, which is, well, I'm storing the vector external from the table. And that's now the default in pgvector. It was extended for a bit, but keep in mind, extended tries to compress, and we can't compress vectors. So it kind of looks like this, right? You have 2 choices, really. You can store the vector in line with all the data within your heap page, or you have a toast pointer to it, and you're storing it out of line. Why am I showing this visual? Well, because of how we access this data, it is going to impact it. Toast is typically, when you think about where toast comes back from, for text data, often you're not searching over your text data. Like you might do some kind of filter for it, but it's often not the main part of your query, at least traditionally. And I know there's full text searches. We could have a whole talk just on that. But this is different because vectors are on the hot path. Vectors are a primary part of your search. So if we have to do additional work to search over it, well, it's going to be costly. But this also impacts, the impact we're seeing is on the planner side because the planner costs things as if the vectors are not in the hot path. So because of this, there is real-world impact. So for example, let's just do a sequential scan, right? I think it's like a million 120-dimensional vectors. I'm going to do a parallel sequential scan. I get 6 workers. I do the same exact thing for 1,500-dimensional vectors, and I get 4 parallel workers, right? Because we don't need as many workers to look over a larger amount of data. Yeah, that's not right. Because what's happening is Postgres is playing the sequential scan, and it's looking at the amount of pages in the heap, not in the toast table. And it's going to see more pages with this one than with this one. Now, there's levers you can pull to speed it up. And in this case, we set min parallel table scan size to 1, and we get 11 workers, which is correct. But I, as the application developer, will not know to look for that because I will admit, I do read the documentation, but if I'm trying to get something done, I'm probably not going to read the documentation. But I think there's some ways that we can improve this. I mean, and for one, there's definitely more work we could do on quantization. But there are some improvements we can do on the planning side and some of the infrastructure side with Postgres to improve how we handle toast estimates. I proposed something last year around this, particularly for dealing with the index creation phase. I'm sure it needs some work. I threw the idea out there. But there's more we can do there. But one of my concerns is that we probably are going to ultimately want to index data that's bigger than 8 kilobytes. And how do we do that while maintaining our ACID properties? We've discussed maybe doing some page chaining or toast for indexes, but even that has trade-offs because if you're trying to load multiple pages into memory on an index search, it can be kind of slow. So we might have to do it, but it does require a discussion to see what will make the most sense. And maybe we also want to allow for the index page sizes to be modifiable, maybe even dynamically modifiable, but I'm sure that's causing some exploding heads. The big thing that's coming on right now that we really need to look at is filtering. Effectively, this is what the cool kids say, but effectively it's the where clause. And it does impact approximate nearest neighbor queries in multiple ways because it may choose, depending on the filter, Postgres may choose not to use the ANN index, or it may use a different index, which actually if you use a different index like a B tree, you might get a better resulting query. Or it may use the filtering after the index. The biggest problem with that is you might overfilter and you might not get enough rows back based upon your ANN search space. So the 2 things that are used for filtering today are partial indexes, which, again, Postgres is awesome because basically you can build the index over a subset of your data, or you can partition your data. But you need to be careful how you partition your data because you might also lead, if you're partitioning not on your filter key, you may still run into that over-filtering problem. The other thing that's emerging is hybrid search, which is typically an overloaded term for combining full text search with vector search. But really, I'd say it's kind of a subset of filtering because you're just basically using two different indexing methods or two different filtering methods to be able to get your information. It is something to keep in mind, though, because I'm definitely now starting to see this more and more because I might want to ensure if I'm doing a vector similarity search over some text data, that the keyword actually appears in that particular text. And if it's a very large corpus, you want to be able to efficiently use the two indexes together. So there's some work to do, both I think on the PG vector side and the Postgres side. On the PG vector side, we've been exploring doing, I'd roughly call it a multi-column index, but the idea is, it's called pre-filtering, but effectively being able to store both your vector and your scalar values and be able to do the efficient search over it. There's some other things out there as well. We apparently do some expensive distance computations because depending on the use of, I believe it is termed junk filters. There's a patch on it on the list. I'm not going to try to attempt to describe it in the few short minutes we have left. Other things as well is, if we're able to keep more of the scalar information in the index, we can do some more of the pre-filtering there. But keep in mind, this is large amounts of data. We might also need to work on those storage problems as well. One quick thing. I didn't mention that, and actually the original HNSW paper, it doesn't posit for anything around updates and deletes of your data. But pgvector supports it. And thanks to vacuum. So if I want to be able to delete a vector, pgvector first hides it, and then vacuum comes by and repairs your graph, and you can actually get this very efficient search. But if you're doing a lot of these updates and deletes, it's going to be expensive. And you might actually see your vacuum process get held up because effectively you're doing a serial index build. So one thing we need to do is parallelize vacuum and pgvector, but it's very hard for an index access method to do that. So proposal, let's make it easier to implement parallel vacuum for other indexes. And we might also want to see if it's easier to implement vacuuming processes around other custom indexes and custom table types. Quick anecdote, for HNSW, it took Andrew 1 week to implement HNSW and 3 weeks to implement vacuum. Telling sign. Real quick, as we're getting short on time, distributed queries. I don't think this is a big deal yet, but it's going to be, particularly when the queries start exceeding the amount of memory you have available on your system. This is probably coming for Postgres in the fullness of time. There might be some other reasons why you want to do multi-node too, based upon how you isolate tenants or isolate information of the data. I have a blog post if you wanted to see all the code on it. I'll have it real quick so it gets screenshotted. It's doable, but the one thing is that where we see the advantage is being able to have asynchronous queries, except that we don't get them right now in the Postgres FTW. When you do the merge append, we're doing it serially. So effectively, I'm doing an individual search on every single Postgres FTW instance I'm connecting to. Hopefully, it's not that hard to add merge append as one of the asynchronous options for Postgres FTW, because that would greatly speed things up. So instead of having to do a serial lookup across multiple servers, you could do it all at once and merge it all at the end. Parallel query for pgvector. It doesn't have it. I think that's okay for now with HNSW. If we kept going down the IVF flat path, IVF flat 100% needs parallel query to really efficiently scale. But we're having an issue as well is that even when we've attempted to implement parallel query in the index access method, Postgres is not choosing it. There's if you go to the pgvector repo, there's some discussion trying to figure out as to why, but this is something that we want to figure out how to ultimately do, because I think that there's certainly cases where parallel query would even make sense for HNSW. Going real quick to Dr. Seltzer's keynote yesterday, hardware acceleration, pgvector has certainly made big use of it, first from compile time flags, and then from some explicit CPU dispatching that was added in the version 0.7 release. And now it's even incorporating some of the SIMD support from Postgres, particularly in the upcoming version 17 release with PG PopCount, which helps with the binary vector comparisons. Big question that always comes up is, well, can we use GPUs for it? That's a big topic. But similar to what we heard in the keynote yesterday, there are probably opportunities. For PG vector, it's likely on the index building, particularly on larger vectors and larger data sets. But we need to make sure that there's effectively efficient transfer of the information between the different areas of memory in order for that to work. So borrowing a term from the day job in terms of dogs not barking, like what are things that maybe we should worry about, but they're not too big of a concern yet? Well, we're still figuring out vectors, but that's not necessarily where the data starts off as. It might start off as a matrix or a tensor, which I will poorly define as a matrix of vectors. I feel like these might eventually make their way to these kinds of databases. So we should think about like how would we solve them? Give an example, like if we're already having enough trouble indexing a vector on a single Postgres page, how do we index a tensor? Storage type and capacity. So what's interesting is that we might see people want to keep their vectors at different levels of storage or different storage with like different performance properties, because it might get very large. Like it's not uncommon for me. I talked to a startup that's storing like 50 million vectors for a transactional application. And again, when I was in the startup world, I'd have 50 million rows of something, but it might take up like 50 megabytes, right? But now I have 50 million rows taking up 50 gigabytes. That's certainly a huge increase. And native vector support in Postgres might help accelerate more adoption. Now, we can see PG vector adoption is going pretty well, but I do hear from people that say running create extension vector is hard. And it might be easy to laugh about that, but it is one extra step in the process, particularly if that extension is something that an administrator needs to install, or you don't have privilege to do within your existing workstation. Now, we talked about a native vector support last year, and the thought process was like, let's just hammer on PG vector to make it really fast, because it's going to go faster as an extension than if we add it immediately to Postgres. So here's my personal opinion of areas we need to improve in PG vector in a prioritized order. And filtering is like the biggest thing right now. Quickly, what happens when you start working with vector data is that you're not searching over the entire data set, you're searching over a subset. We should make sure that we're able to have filtering methods that are able to do the vector search and efficiently filter through it so we're not doing too much work later. All the others that we talked about, we could argue where they go in order, but these are all things that we're certainly hearing. But really what's helped as well is the combination of the PG vector community and the Postgres community, which there is overlap there, certainly, but it's been good to see people with strong knowledge of the machine learning information combined with the strong knowledge of the database information. And these are all examples where knowing how Postgres works really well has given dramatic performance gains. One of them was just for HNSW, between 050 and 051, improving the locking mechanisms greatly sped up the builds and made it much more usable. So let's all work together, because what I said last year at this time was that we can clearly see there's a flood of net new data generation coming to Postgres, or just the flood of net new data generation, period. We'd love to see it in Postgres. So let's make sure we put Postgres in the best possible place to get that data generation. And we've done a pretty good job. Like, Postgres is very popular for vector search. There's still more to do. And with that, we are at time. Thank you. Well, I guess we have 2 minutes. So I'm here all day, as you may know, but if there's any questions now, happy to answer them.
You showed that graph where PG vector was down to the left from last year. Do you have anything updated with where the newest versions of PG vector kind of fall?
Yeah, so on this data set, it's going to be on a single thread, it's probably going to be somewhere in this range, I think. One area that I think that we don't test enough or don't talk about enough is how PG vector performs under concurrency. Because I'm not trying to redirect it, I just want to state a reality, is that when you see PG vector and Postgres going on concurrent workloads, you see a very different story, and you actually see a lot of the specialized solutions fall off there. So I think that's something we do need to tell a little bit better. But at least for a single-threaded, like I said, it's like more in this range, if I'm eyeballing it correctly. Yeah. And there's certain things like, there's certain in-memory algorithms like it's just not going to beat, and I think that's completely fine, but you're also solving different problems at that point.
Yeah, I have a question. During the talk, you mentioned that you've been talking about changing this page size, and you said that it doesn't actually work for indexes or something like that.
Yeah.
Are you actually sure about that?
Yes, there's a thread on it from, I want to say September. We can change it, like it's hard-coded, but I think the comment that came back was there may be a lot of ramifications for this, so it requires further study.
Yeah, okay.
Yeah.
I mean, like, there definitely is like consequences of like doing that, right?
Yeah.
Okay.
So it's not, so I'll rephrase it that we can't right now until we do further study, but Tomas, I heard you want to do the further study, so that's great.
Right.
By the way, just a quick shout out to Tomas since he asked a question. I think it's the memory allocation one. Tomas actually contributed last week to PG Vector. It was merged yesterday.
So once we build the indexes, like IVF,
Yep.
do we have to rebuild it through time? Like how often?
So one of the design principles of PG Vector is don't rebuild. We're trying to modify the data format so that way the only times you need to rebuild are, let's say you want to take advantage of quantization, then you'd have to build a new index. But we're trying to keep the data format consistent.
So don't you think that new data will affect the precision?
So new data what?
Will affect the precision? Like,
So it depends. Precision's impacted, like the challenge with recall and precision is that there's all sorts of things you need to consider. Like, my opinion, not to like throw it over to the machine learning side, but it's those machine learning folks that are impacting the precision the most and the recall the most, because if they build better models, then there's less work we need to do on our end in order to be able to do those comparisons. But at the same time, we also need to make sure that we have the tools available to help expand that recall. So I think where we might see a rebuild is if PG Vector needs to add an additional index access method. Let's say an algorithm comes along that's like perfect for Postgres. But again, that's shifting data over. It's not rebuilding the data that's in place. Cool. Well, please don't let me keep you for lunch. Thank you for attending. I'm here all week.